All right, welcome to today's lesson on the tangent function, which is the last circular function we get to look at in methods. Um, and it can be a little bit tricky to begin with, but hopefully you'll get the hang of it. So tangent, and if you don't know what tangent means, think about when your teacher goes off on a tangent discussing other things. That means that they sort of touched on a linking topic and then went off in a completely different direction. So when we look at a circle, a tangent to a circle is a line that touches a circle at one point and then goes off in a different direction. So it could be there, or it could be there, or it could be there. All right, now interesting things about tangents are that when you start from the center or the origin and go out to where it touches, that angle there is definitely a right angle. Okay, so the tangent is perpendicular to the radius always. All right, so remember that because it's a very key part of this. Okay, so I'll just erase those tangents and we'll talk about how it happens on the unit circle. So I don't have a historical lesson for you this time. All I can assume is that the people who just made this up were looking for interesting things to do with circles and angles. All right, so here we go. The tangent on the unit circle is actually drawn as a vertical line here. All right, I haven't drawn it very well, but it touches there at 1, 0. Or it can be drawn on the opposite side here. All right, now it can extend infinitely in each direction. Okay, so that's the tangent line. Now, if we go back to our point on the edge of the circle, and we have a radius drawn from the origin to that point there, we know that that vertical height is sine, and that horizontal distance is cosine of whatever that angle is, and we'll call that theta. All right, and also remember that this angle in here is a right angle, just like the angle here is a right angle, because across the bottom or across the x-axis there where it hits out to where it hits the tangent, that's the radius, and the radius always meets the tangent at right angles. All right, so there's some background to bring us up to speed. Now, where the tangent function appears is here. If I were to extend the hypotenuse of this triangle inside the unit circle, this one here, so if I were to extend this blue line past the edge of the circle and continue it to where it hits the tangent, all right, so it would look like this. I would have the hypotenuse looking like that. This point here, all right, we'll call this point C, is a certain distance above the x-axis. And this distance is the tangent function. All right, so to recap, when you map a point on the edge of the circle, its height is the sine function, its horizontal distance is the cos function, and if you were to extend the line through the point to where it hits the tangent, the total height of that tangent line would be the tan function. All right, so it's not as intuitive as the other two, sine and cos, but it still makes sense in a picture. All right, so this is the height here is the tan function. Okay, now to show you a little bit more information about it, if we were to use similar triangles, so I'll just name some points here. This point here is the origin, it's called O. This point here is our point we're interested in, and we'll call it P. All right. We'll call the bottom here, we'll call that D just for a letter, and we'll call that point there, we might as well call that A. All right, so now I have two triangles. The first triangle is the small one inside the circle, and that's called OPD. The second triangle is a larger one and partially outside the circle, so O to C to A. All right, O to C to A. Now, these two triangles are similar triangles. The big one is just an enlargement of the small one. And they're similar, we know they're similar because they share this angle and they each have a 90-degree angle, which automatically means the third angle is the same, which must mean that the two triangles are similar. Right, and similar, if you've forgotten, means that each corresponding side is in the same ratio to other corresponding sides. All right, so using a bit of those similar triangles, we'll try and establish the ratio that tan is. Well, you might remember this from year 9 and 10, but I'll show you why it works. So looking at similar triangle OPD, which is the small one on the inside, and triangle OCA, which is the big one that includes tan, all right, I'll use CA over OA, and I'll explain why I'm using those. And I know that the similar triangles are in the same ratio, and because I've specified two sides in the big triangle, I have to specify the corresponding sides in the small triangle. So CA corresponds to PD and OA corresponds to OD. Now, the reason I used CA is because that was tan and I wanted to know what it was. The reason I used OA is because that's the only other side in the big triangle that I know, and it's 1 because it's actually the radius. PD I know is sine, and OD I know is cos. So this establishes the actual definition of tan for us. It is tan equals sine over cos. All right, so for any angle, tan is sine over cos. And you just need to remember that when you're finding tan, you're finding the vertical height of the tangent where the point has had its radius extended through the edge of the circle until it hits the tangent. All right, so this picture here might be really valuable to put into your book and annotate as tan so that you know what you're finding. All right, now there's a few key pieces of information that you need to remember about tan. As you can see, when this point moves around the circle that way, we can see that the tangent's going to have to be taller to accommodate for the extra angle, right? So up here, you might have another point, and if we extend it past, it'll be all the way up, hit the tangent all the way up there. All right, but what happens when the point is directly on the y-axis vertical? All right, you might know that this line then and the tangent line will be parallel, and therefore this extension will never ever hit the tangent. All right, in this case, we can call that undefined. All right, so tan actually has two values which are undefined. And you can see here that it's when the angle is 90 or pi on 2, and it's where the angle is minus 90 or minus pi on 2. All right, now you already know that we can do multiple rotations of the unit circle. So if you ever asked to find tan of a big angle that goes around the unit circle more than once, you're looking for multiples of pi on 2 or minus pi on 2. So that might be things like 3 pi on 2 plus or minus going forwards or backwards, or it could be 5 pi on 2 plus or minus going forwards or backwards, and so on. All right, anything that has a multiple of pi on 2 is going to leave tan as undefined. All right, so let's have a quick look at an example. All right, it's this one here where tan of pi. I want to know what tan of pi is equal to. Okay, so first of all, I've got my unit circle on the right hand side here. I'm going to map out where the angle pi is, and I know that pi is there on the x-axis. So I'm going to need to draw my tangent function on the left-hand side, and I can see that that would be the point right there on the radius, and I can see that it's actually dead on the tangent function already. So there's no room for me to draw this extension in the gap that I have here. So tan of pi, hopefully you can see, is going to be actually equal to 0. All right, there is no extra dotted line needed to join the point up to the tangent function. All right, so that means that the distance is 0. Okay, we'll try a couple more. Here is an example of what about tan of 7 pi on 2. All right, so again, we'll map it out on the unit circle. So I've got 7 pi on 2. I'm going to choose to think about that as it's going to be 2 pi plus, what's that, 3 pi on 2. So if I break it down, that will be 2 pi is the same as 4 pi on 2 plus, and then to get to 7 I need an additional 3, so that's 3 pi on 2. Alright, so I know 2 pi is a full rotation, so I've already gone all the way around and back to the start. Then I have to go 3 pi on 2 more, so I know that that's half, half again, and another half. So there is my point. It's vertically downwards, and I knew from the example earlier that if I extended this dotted line up, given that it's vertical down and the tangent line is also the same, they're parallel, so therefore tan of 7 pi on 2 is undefined. They will never meet. All right, so to recap, this drawing here is going to be pretty important because you need to remember what it is. You need to remember that you're finding the vertical height of the tangent line when you extend the radius through the point on the edge of the circle, right? That's the tan function. We've shown how it's equal to sine over cos. So if all you know is the sine and the cos, you can still find the tan, right? Or you can use your calculator to type in an angle or type in tan of the angle and hit go, and it will spit out your answer for you. Okay. Try and work by writing down multiples of the angles if you're given a compound angle like this, where it has multiples of 2 pi or different rotations, so that you can clearly see what the underlying problem is. You can see here that the 2 pi didn't make any difference to the answer. All right, so hopefully that makes sense. If you have any questions, let me know.